Today I'm going to be showing you that light is actually made out of small little particles.
Some of it's due to just the photons hitting the surface.
From Planck and Einstein, we learned that light comes in discrete packets of energy, called a photon.
That means that each photon should have to decide whether it's going to go through one slit or the other.
Now, how could they interfere with each other because there's only one in the device at any one time?
Welcome to quantum physics.
We now have to accept that light obeys wave-particle duality, meaning it is both a particle and a wave at the same time. Confused? You should be.
Hey everyone, I guess I was confused. In the past I've assigned particle properties to light, but apparently I'm not the only one. So why is everyone confused? Well, to find out, let's start by looking at history and see where most of the confusion about particle-wave duality originated from. Whether light was a wave or a particle has been the subject of fierce debate since the end of the 17th century. When Christian Huygens published a paper on the wave theory of light in 1690, most scientists of his time did not agree to his views, among which was one of the most prominent scientists of that time, Sir Isaac Newton. In 1704, so about 14 years later, Newton published a book in which he explained the behavior of light in terms of small, fast-moving particles. And for about 100 years, both the particle and the wave description had their own fan base. However, in 1801, Thomas Young demonstrated that light behaves like a wave and that the colors of light are in fact related to wavelength. And he did this by performing what is now generally referred to as the double slit experiment. Again, about 60 years later, the work of James Clerk Maxwell showed strong evidence that light should in fact be an electromagnetic wave. So at the very beginning of the 20th century, there really wasn't much debate anymore. Light consists of waves. So where did things get confusing again? Well, in 1905, Albert Einstein wrote a now famous paper on the production and transformation of light. In this paper he combines experimental data from various sources, connects them and discusses some of the theoretical consequences. And one of his conclusions is that the energy contained in light is not continuously distributed in space, but as he states, it consists of a finite number of spatially localized energy quanta. He proposes that these quanta are indivisible and can only be absorbed and emitted as a whole. And the arguments to support his claims are mainly based on the results of an experiment that is now better known as the photoelectric effect. To understand how Einstein came to his conclusions, let's take a quick look at the essence of the photoelectric effect and what exactly points to quantization of radiation. The experiment is generally performed in a high vacuum with two electrodes. One of the electrodes is covered with a layer of a specific metal, for example cesium, and when we irradiate this metal with UV light, electrons can be expelled from it. We know this because we can measure the potential difference that arises between the two electrodes. Basically because the negatively charged electrons go from one electrode to the other. And so we can do various experiments on this system, like vary the wavelength of the light while measuring voltages and currents, or deliberately change the potential to see at which field values the flow of current stops. Now the thing is that this phenomenon only occurs when the frequency of the light used for irradiation is above a certain value. For example, the effect exists for UV light, but not for visible light or infrared light, not even if the intensity of the latter radiation is very, very high. When the frequency of the irradiation is above a specific threshold, however, we can measure the effect even at very low radiative power. So by changing the potential difference between the two electrodes, we can also measure the maximum kinetic energy of the emitted electrons. And it turns out that this maximum kinetic energy is dependent on the frequency of the light and increases with higher values. So now we're faced with the following. We observe emission of electrons, so discrete entities, from the metal by irradiation. And in order for these electrons to escape from the metal surface, each of them needs a certain amount of ionization energy, which is more or less a constant. But apparently they're also left with a certain kinetic energy, which is dependent on the frequency of the light. And this suggests that the total energy needed for this is supplied to the electron as one discrete package with a certain amount of radiative energy. So part of it's used to escape the metal, and the part that's left over remains as kinetic energy to the electron. And so the experiment strongly suggests that light consists of small chunks of energy rather than a continuous stream. Now, it's these energy quanta in light proposed by Einstein that are referred to as photons by many people today. You might now think that the name photon is an invention of Einstein, but it's not. The name photon was introduced 21 years later by Gilbert Lewis, who used it as the name to describe a hypothetical new atom that plays an essential part in every process of radiation. And I guess that's how it sticks in everybody's mind, including mine. A photon apparently being some kind of light particle. And I guess partly also because of the name it was given by Lewis. Electron, proton, neutron, photon. The corpuscular or particle view on light, reintroduced by Einstein, still causes a lot of confusion and influences fundamentally how many of us look at light. Drawings of emission and absorption processes show discrete little wave packets. Complex experiments with light are explained in terms of photons moving through slits and prisms and then hitting detectors. Stimulated emission is described in terms of light particles, 1 photon in, 2 photons out. The corpuscular description of light is literally everywhere, and almost every science video on YouTube is about light being a particle at some level. But is it correct? In this video and the follow-up video, I want to leave the corpuscular or particle view behind me and try to explain light and its properties purely as the result of wave phenomena. The reason I made this video is that hopefully it can lead to better understanding, initially for myself, but of course also for others. Personally, I do think that the energy in light is in fact discontinuously distributed in space, as Einstein initially concluded, but not because light itself consists of packages or photons, but because of a direct result of wave phenomena, in particular those related to coherence. As will become apparent, coherence is actually a pretty complex subject to explain in simple terms. So that is why I want to use at least 2 videos to explain it. There are 2 fundamentally different types of coherence behavior: temporal coherence and spatial coherence. In the current video I'll mainly talk about temporal coherence, a phenomenon related to spectral bandwidth. So in the case of light, temporal coherence is about which colors or frequencies are present. And later in the video I'll demonstrate experimentally how we can observe and measure temporal coherence in light sources. In video 2 I'll discuss spatial coherence, which is about the geometry and how aspects like the size of the emitter, the wavelength and the distance from a source can create a spatially uniform field in a specific area. And of course, I want to take a few sidetracks to see if we can get a tiny step closer to understanding the particle-like behavior of electromagnetic radiation. When we talk about coherence in wave phenomena, for example surface waves, we refer to how strongly points on the surface move in sync with each other, both in space and time. Waves aren't static entities but move at a velocity over the surface in a certain direction. Now, I'm not much of an animator and this is of course a static image, but the idea here is that the waves shown here are moving from left to right. This here is an example of a very regular linear wave, and if we look in the direction of propagation, every point on the surface moves with exactly the same frequency. So apart from any phase differences, the movements of all points are synchronized and so they're directly related. And we call this wave temporally coherent because it does not change in time. Also, if we look in the direction transverse or perpendicular to the direction of wave propagation, we see that all points move in unison. And this means that this wave is also spatially coherent, because spatial coherence is about the relation between points in the direction transverse to wave propagation. So, if we were to keep track of a particular wave on the surface along the direction of propagation, it will be here at a specific time, and at a later time the same wave will be some distance further. And of course, this distance depends on the propagation velocity. This illustrates how in temporal coherence distance and time are related, especially if we ignore damping or friction for now. Okay, I admit this is a pretty boring wave, so let's make things a bit more interesting. Here we again have a linear wave moving in the same direction, but now the wave has a variable frequency. If we observe at one specific point in space again, we see that the frequency changes in time. The same if we compare the waves at different positions along the direction of propagation. And if we were to compare movements of points on the surface in this direction, we would observe that these are actually not in sync anymore. In other words, because there is more than one frequency present in the wave, we've lost temporal coherence. However, this wave still is completely spatially coherent, because in the transverse direction all points are still moving in sync. If that were not the case, for example in this particular wave, if we move in the transverse direction, we also lose coherence at every point on the surface. And so this wave is both temporally and spatially incoherent. Now let's return to the spatially coherent wave. You might argue that for this particular wave, the degree in which temporal coherence is lost depends on the time interval during which we observe the wave at a particular location. And that is indeed correct. If this time interval is small enough, we might actually not see any significant differences in amplitude or frequency. The same of course is true if we compare the waves only over a very short distance on the surface. So for temporal coherence there is a time and corresponding length at which you can say that any loss of coherence or synchronization is acceptably small. And these values are generally referred to as the coherence time and coherence length. Now for spatial coherence we actually have something similar. If we just examine a tiny fraction across the wavefront, we will still of course observe phenomena due to temporal incoherence. But due to the fact that this area is very small, the wave behavior within that specific area will actually be uniform. So whereas the degree of temporal coherence can be quantified by a coherence time and length, the degree of spatial coherence can be quantified by an area of coherence. I'll dive deeper into the subject of the area of coherence in the second video. In this video though, I will assume perfect spatial coherence in all examples. The main reason for strictly separating the two is convenience, because for spatially coherent waves, whether they are in 2 or 3 dimensions, the behavior can always be described in one-dimensional plots. And so by assuming perfect spatial coherence, we can simplify things quite a bit when we want to discuss the essence of temporal coherence. Now this temporally incoherent wave contains sort of a frequency gradient and therefore contains multiple frequencies. However, this is not a very good depiction for the electromagnetic waves of light. For one, because the electromagnetic field will be something that propagates in 3D space. Also, there will be an electric and a magnetic component to it and a polarization direction. But if we consider perfect spatial coherence also in light, all of this added complexity is actually completely irrelevant, because the field passing any area of coherence will be the same for all points in that area. And so we can still describe the behavior in one or more one-dimensional plots. The electromagnetic field in light is actually the linear sum of many individual smaller waves. And that is because this field at any point in space is the sum of emissions by excited state atoms or molecules that fall back to a lower electronic state. And when they do, they can emit a small electromagnetic wave, which adds to the total field. Now this schematic image might give you the impression that waves actually interact with each other or meld together, but that is not the case. In a linear medium, waves don't interact, they just momentarily interfere. For example, take the case of two temporally coherent laser beams. Their fields might show interference in a specific area when they cross paths, meaning that their fields add up or cancel out for a brief moment, but after that the waves will go their own way unaltered, as if nothing happened. Okay, so what is a photon in this depiction? Well, it's actually the emission of a certain amount of radiative energy by the emitter. Just to be clear, I'm not referring to the resulting electromagnetic wave as the photon. I'm referring to the conversion process to electromagnetic energy. This process is actually quantized and is governed by the difference in the energy levels allowed within the emitter. So in emission, a photon is just the creation of a certain amount of electromagnetic energy. As for the electromagnetic field emitted, this immediately becomes part of the total field and will generally become inseparable from the total soup of electromagnetic field waves that may already be present. Now, I drew the emission process as occurring in all directions, which is not necessarily true, because it can be sort of directional. But due to the nature of the electromagnetic field, it can also not be purely unidirectional either. It has to spread out in space as it propagates. And a logical question you might have now is, how can we absorb a discrete amount of energy if waves spread out in space like this? Well, let's leave the explanation to that question for video number 2. An intrinsic aspect of light is that it always contains multiple wavelengths or frequencies. There are several reasons for this, and I will just name a few of them. For example, emitters like excited state molecules are always moving. In a gas, for example, their velocity is generally in the order of several kilometers per second, and this causes a Doppler shift in the frequency of the emitted radiation. Also, there are considerations related to the Heisenberg uncertainty principle for time and energy. So short emissive processes have, by definition, a higher uncertainty in energy and therefore in wavelength. But maybe I'm getting ahead of myself. The most important thing to remember is that every source, even the fanciest laser, emits multiple frequencies, if only because every emission process occurs in a finite time interval. Let's focus on what temporal coherence looks like if we consider the linear addition of waves in one dimension. In other words, in the case of spatial coherence. Here you see a hypothetical infinitively long harmonic wave with just one single frequency. So if you look at the spectrum, it's actually just a single line corresponding to this frequency. Now let's see what happens if we consider two waves with a slightly different frequency. Here you see how the individual waves look, and here you see what happens to the linear sum of the two waves. At points where the two are in phase, we get the highest peak to valley differences, but as the waves gradually go out of phase, we observe destructive interference, which causes the amplitude to go down. And at some point, however, they will get in phase again, and so what we observe is a beat frequency, that is the difference between the two original frequencies. Now, let's add a few more frequencies to this. In this case, 7 regularly spaced frequencies. At points where all the frequencies are in phase, we get constructive interference again, and we see the same kind of regular pattern appear of areas where all waves are either in or out of phase. Now, as the next step, let's weigh the contributions of these frequencies such that their amplitude becomes smaller as they get further away from the central frequency. What you observe now is that the interference pattern consists of these little separated wave packets with very little activity in between. Now this is where I want you to take a big step and consider the following. What would happen to this interference pattern if we did not just use 7 frequencies, but a continuous Gaussian distribution of frequencies and add all of these up? Well, if we do that, we would arrive at the following wave pattern. Just one single isolated wave packet, only at the point where all the waves are in phase. Now some of you might be surprised and think, well, where have all the waves gone? Some of you more into math and cats may think, ah look, Fourier transform kittens. So cute. And those of you who've seen the most recent Physics Explained video on the uncertainty principle will probably say, yeah, of course, I knew that. In the case of a Gaussian frequency distribution, the coherence length is related to the half-width of the spectral distribution by the following formula. What this formula basically points out is that the coherence length is inversely proportional to spectral bandwidth. So just a quick illustration of why this is. If all frequencies involved are very close together, like in a laser, it will take a long time for the waves to go out of phase, and so the waves will be coherent over a long distance. Whereas if we have a very wide distribution of frequencies, the distance over which the waves are in phase is actually only a few wavelengths long. Now, if you casually look at these images, you may think, are you now trying to tell us that radiation automatically comes in discrete packages because of spectral bandwidth and decoherence? Well, actually, no, I wasn't. I was only trying to prepare you for an experiment in which we can measure the coherent length in light. But of course, it's a tempting thought. Very long packages in coherent radiation from a laser, very short packages for broadband radiation. But that would be looking for particles where there actually aren't any, because this type of behavior is purely the result of wave principles. Anyway, about the experiment that I just mentioned, with it we can measure the coherent length of various light sources. For the experiment I used a Michelson interferometer, shown here schematically. Light from a spatially coherent source is directed towards a beam splitter, where it's split into two paths. The light then hits the two mirrors, which reflect it back to the beam splitter, where it's recombined and projected on a CMOS sensor. One of the mirrors has a fixed position and the other has a variable position, which allows us to change the difference in length between the two paths. Here's the actual setup I built. It's quite simple. Here is the light source pointing into the beam splitter. These are the two mirrors, and to the left is the CMOS sensor. One of the two mirrors is placed on a linear translation stage so that the length of this path can be varied. For the first experiment I built a spatially coherent white light source. This sounds kind of special, but it's not that difficult to make. It just consists of a white LED, a tiny pinhole in front of it, a collimation lens and an aperture. Because of the spatial coherence, the beam exiting this source has a uniform field across the beam area. And as a consequence, the light from this source looks kind of weird because it's very parallel over long distances. Now, with this spatially coherent source, we can look at the temporal coherence properties of white light. Here you see the camera image where the length of the two arms of the interferometer are exactly equal, and we can observe a clear interference pattern. Now, getting this image is not trivial because the accuracy required for matching the two path lengths is only a few wavelengths. And this is because the light is spectrally broad and the contained frequencies will go out of phase very quickly. The reason that we observe an interference pattern is the following. If the arms of the interferometer are equal, every electromagnetic wave from one arm, regardless of frequency or phase, is basically in phase with the wave from the other arm. And therefore, this will lead to visible constructive and destructive interference around the point where the arms have equal length. And the reason why we can observe this pattern directly from the CMOS sensor is that the two mirrors in the interferometer are slightly tilted with respect to each other. And this causes the interference patterns due to temporal coherence to spread out over the CCD sensor area. You can clearly see how the different wavelengths start to go out of phase quickly when we move away from the point of equal path length. In fact, by using narrowband interference filters, we can look at the separate frequencies or colors present in the pattern. We see that every frequency has its own interference periodicity. The blue light with the shortest wavelength has the smallest spacing, the red light with the longest wavelength has the widest spacing. And the white light interference pattern is basically the sum of all frequencies or colors. Now here's a screenshot again of the interference pattern that we observe. If we now discard the color information of the camera for a moment and just look at the intensity, the image will look something like this. This image allows us to extract approximate intensity information and plot it as a function of distance. And you see that we can now very roughly estimate the coherence length of the image. With the average wavelength of the light being around 500 nanometers or half a micron, the coherence length of the white light is just about 2 wavelengths long, so about 1 micron, extremely short. Okay, now let's try a different light source, in this case a laser diode. Now, stimulated emission only takes place at very high field intensities in the laser cavity. In other words, at relatively high operating powers. However, if we operate the device at very low currents, it basically works like a normal LED and only shows spontaneous emission. So let's take a look at both operating modes using the Michelson interferometer. We'll start out with a low operating current. The diode now operates as a normal LED, so no stimulated emission. And here you see the camera image again, when the two arms of the interferometer are set to equal length. In the images, the interference lines are spaced much closer together, and that is because I placed the two mirrors in the interferometer under a larger tilt, so we can look at decoherence over a larger distance. And you can now observe that coherence extends over a larger number of wavelengths. We can do the same measurement of coherence length here. We can take a screenshot of the interference pattern, convert it to an intensity plot, and then estimate the coherence length. And now it's almost 4.5 microns, which is about 4 times longer than in the case of the white light from the LED. Now let me show you what happens if we increase the current through the laser diode to the point where it actually starts to laze. So here I'm turning up the current, and because the intensity of the light output is much higher now, we either need to decrease the shutter time of the camera or attenuate the light by means of a neutral density filter. But look what happened to the interference pattern. Now suddenly it's everywhere. Whereas in the previous cases it was tricky to find the interference pattern, I can now go wild on the micrometer of the linear stage and never lose the interference from sight. We can actually extend the difference in distance between the two paths from centimeters up to several meters. And this can be achieved by carefully setting the current of the laser diode to a value of very stable operation. And so this illustrates the extreme difference in coherence length between a source operating in spontaneous emission mode and stimulated emission mode. In the latter case, the source can evidently create a spectral distribution so very narrow that coherence is preserved over distances of several meters, which is 1,000,000 times longer than in the case of spontaneous emission. So I want to pause my presentation here, and I will continue in a second video, in which I will, among other things, discuss spatial coherence in more detail. And I will of course continue the discussion on how phenomena related to coherence and interference can create a non-uniform distribution of energy in space. I can assure you it's going to be fascinating.